Presentation is a subset of yesterday's presentation. Professor Young-ho Park. 90% of my presentation was given by yesterday. so yes, most part is the summary of yesterday's presentation. Okay. In 1995, Calderman and Sloan published a paper. In the paper, they studied codes of a finite field GP, and they lifted the codes to a code over G sub P to the E, and then they continue. They lifted it to a periodic codes. And in the paper, they presented these three interesting codes: two-adic Hamming code, and two-adic Golay code, and three-adic Golay code. And they are all self-dual, and they are all MDS codes. And after 10 years, 2005, Stephen Doherty and Sunghyu and Young-ho Park published a paper. They compute weighted distribution of the projection of these three codes to finite codes, and they computed weighted distribution. They computed the weighted distribution of these two cases, but I mean the projection of weighted distribution of the projection of these two codes. They completed these two cases, but they didn't complete this two-adic Golay code. So in this presentation, I will compute this open case weighted distribution of the projection of two-adic Golay codes to these finite rings. Okay. And I'll give some basic definitions. We use G sub Q. Q is the P to the E, and E may be infinite, so this is a unified notation. And we say linear code C is the submodule, and we define weight and minimum distance. And if Q is finite, then we can calculate weight in numerator of a code C. Okay. And if C is a code of periodic integers, because periodic integers is the principal ideal domain, so every code C is a free code. So we can easily define that the dimension of C is just the rank of C. But if C is a code of a finite ring, then the dimension is not defined simply like this one. Yesterday, Young-ho Park explained the dimension, how to define dimension. But in this slide, in this talk, we only consider a free submodule of C. So in this case also, we simply define the dimension of C is just the rank of C. And we use this notation, and okay. And in this ring, we represent an element of this ring is periodic expansion. And in periodic integers, we have we describe an element. This one is infinite series. And we define projection map from periodic integers to finite ring, just natural projection. And if this ring is larger than this ring, then we also define natural projections. And we define lifts of codes. We say C1 lift to C2. If C2 has a generator matrix G2 such that projection of G2 is a generator matrix of C1. So if we have a PID code, then we have infinitely many projections to finite rings. So if we have a PID code, then we have a series of lifts of codes. And we use the natural inner product, Euclidean inner product, and we define dual code and self-dual code. And in self-dual code, we have this kind of weight enumerator formula. Okay. I'll give an example. For two-headed Hamming code case, x to the 7 minus 1 can be factored with these three polynomials, and a is PID integers, and a satisfies this quadratic equation. And using this second polynomial, we make 7 for cyclic code, the same as we do construct a cyclic code in finite field. And then we extend the 7 for cyclic code, then we obtain A45 self-dual Hamming code. This last column is the extension, and this one is the generator matrix of 7 for cyclic code. And we extend the last column, then we have a generator matrix of self-dual code. And we have a self-dual Hamming code, two-headed Hamming code. So we have a projection. We have infinitely many projections. So we have a series of lifts of codes. And H is a self-dual code. So we have this kind of weight enumerator formula. So we can define CIs. So in this case, we can easily compute this coefficient CI. Okay. And two-headed Golay code case, also we can factor this polynomial as three polynomials. And pi1x has a degree 11 polynomial, and A satisfies this quadratic equation, two-headed integer. And similarly, we make a cyclic code using pi1x, and we extend the generator matrix of pi1x, adding all one column, similar to the previous slide. So we make 24, 12, 13 self-dual Golay code. So we have a two-headed Golay code. So we make natural projections. So we have a series of lifts of codes. G1 is just a binary Golay code. So we know our objective is the calculation of all the weight enumerator of for these finite cases. And G1 is a Golay code, so we know the weight distribution. And G2 is the Golay code over G4. And we have a generator matrix, so we can calculate this case. We can easily calculate this case. And then if E is greater, then the complexity grows very fast, so we cannot calculate. So, and the weighted enumerator has this form, and in this equation there are 13 unknowns. So we use weighted distribution notation. We denote this as a weighted distribution, and in the 2000 paper they proved this one. All projection codes minimum weight is 8, and the number is 759. This value is constant for all E, and there is no code word with weight 9 for all E. And so we want to determine certain unknowns, so we determine the 10. We want to determine certain unknowns, so we have to obtain certain conditions. So this is 10 conditions, because a sub 0 is always 1. This is a 0 vector, and also in the paper, A10, A11, A12 is constant for E is greater than or equal to some constant number n. And they calculated, in this case, the n is equal to 7. So we only have to calculate A10, A11, A12. For E is equal to 3, 4, 5, 6, 7. So remaining is the calculation of these values. And G3, G1, we calculated G1, G2, and for the next case G3, using the magma command, weighted distribution, we can easily obtain in this value. But the running time is almost 4 hours for this case. The running time grows very fast, so I expect that the running time of G4 using this command is more than 2 years. This is just my guess. And so, and also in the magma function, number of words were partial weighted distribution, but these functions only applied for codes of finite fields, so not applied for codes of rings. So we have to make a program. Okay, so the first algorithm is the computation of A sub omega, the number of code words with weight omega. If G is a standard generated matrix for the NKD code, then we calculate all the linear combination, T linear combination up to omega. So we calculate all the linear combination. This is just simple algorithm. Okay, and if our case is a self-dual case, so we have a two generated matrix. This is a parity check matrix. Then we have this kind of two generated matrix. In this case, we can reduce the complexity, and because if C is weight omega, then the first part of C1 is less than or equal to omega over 2, while second part is less than omega over 2. Using this idea, we consider a linear combination of rows of generator matrix up to omega over 2 or up to omega over 2. So we use these two metrics. So we reduce the complexity. And then we we continue algorithm 2, so we a little bit improve previous algorithm, because this part is identity matrix. So in the linear combination, this part is always weight T, and also this part is in this matrix, this part is always weight T. So we use only this part. So, and then we count code words of weight omega minus T in this matrix. So because this is always this is identity matrix, so we use right hand, and in this matrix we use this left hand. So we consider linear combination of this matrix and this matrix, and we count code words of weight omega minus T rather than omega. So anyway, I calculate the number of calculation. This is the formula. As you see, this formula has exponential function, so the complexity grows very fast if E is grows. So in this case, if E is equal 7, omega is 12, then 2 to the ET is 2 to the 42. So this is very complex. So, and this is my idea. In the previous algorithm, we calculate linear combination, but in this case, for each column, we have a zero set. This is the this M1I prime, M2I prime is the coefficients of this matrix, and we counted the number of solutions in these homogeneous equations. So we and this is the formula, and so this zero set is the number of zeros. We want to make a code word C. Weight is omega minus t. Then the number of zeros and the number of 1. The number of 1 is omega minus t, and number of this length is k, and k minus omega minus t. So this is the number of zeros. This index r, the cardinality of index I is k minus omega minus t. So we can easily calculate this part because this is the just system of linear equations. And first we find this set and we subtract this non-zero part. So and then we calculated using this formula. We calculated these values. So the time is very fast because the most complex part the running time is 135 seconds. So we complete these values. Okay, thank you very much.